So now we come to the conclusion of working with vectors and matrices, and the whole point being that we will manipulate um, vectors in space by being able to transform them, rotating them, or translating them linearly. But here, let's start with an example. We'll say we have a vector v, right? And this is 1x hat plus 1y hat, right? And that can also be written as v is equal to this vector 1, 1 in matrix form. So here we have this thing called a rotation matrix. This will rotate whatever you multiply it by, supposedly counterclockwise. This is counterclockwise. So let's do that. Let's take a and multiply it by v, right? So it'll be 0, negative 1, 1, 0, and 1, and 1. So that equals 0 times 1 minus 1 times 1, right? And 1 and 0, right? And then 0 and 1. So that gives 1. So this equals negative 1 and 1, right? That's a plus right there. So we went from this matrix, this vector at 1 and 1, and we can see how the new vector is moved 90 degrees counterclockwise here to negative 1 and 1. So it did rotate it, and that's really the point of working with these matrices and vectors. So we can shift them, rotate them, scale them. Now, if we did this twice, it would be a squared times 1, right? Now, since a and a is the same, that would probably take us the same place. So backwards and forwards is the same thing. But what if we reflect it, right? So let's call this one R, okay? So what if we rotate and then rotate and then reflect? Would that be the same as reflect and rotate? So let's see how that's done. So rotate, we are already seen it ends up with this vector, right? So let's go ahead and take that vector, which was v equals, let's call this b2, equals x equals negative 1 and y equals 1, right? So let's take that and reflect it by multiplying it by the reflection operator, or matrix. So that would be 1, 0, 0, negative 1, and then negative 1, 1. So what does that look like? Negative 1, 0, 0, and negative 1, right? So here we see we're going to get a vector and it's going to end up at negative 1 and negative 1, right? Just as we expected. It was going to reflect it across the axis, right? So here we are. So that's good, right? And it just looks like another rotation. But actually this is a reflection. So let's do it the other way. Let's reflect it first and then rotate it. Okay, let's go to a new page here. So remember we had our original vector v, which was equal to 1 and 1, right? So now we have this reflection vector matrices is 1, 0, and 0, negative 1. 1, 0, 0, negative 1, multiply it by v1, right? So 1, 1, and that's going to equal 1, 0, 0, minus 1, right? So, and then we're going to take that vector, the resulting vector, this one, and we're going to rotate it, right? So let's call this v2. Again, let's call this v2. then so we're gonna rotate V2, right? So matrix. So what does rotating matrix look like? The original one we use, the counterclockwise. So it's going to be 0, -1, and 1 and 0. Zero, -1, and 1 and 0 times V2, which is 1 and -1, and that equals 0 plus 1 and 1 and 0. So clearly V3 here looks different from the V3 that was here, right? Because this V3 is what? This V3 is -1 and 1, right? Whereas we'll call this one V3 prime is 1 and 1, right? And we can see that that is that would be, first it would be a reflection from our first vector, which would be 1 and -1, so that goes here, right? And then when we rotate it, it goes back here. So it comes back to the original vector, 1, 1, because we started with 1 and 1, right? So we can see that when working with matrices and vectors, when we have something like A times B is not equals to B times A, right? These are the two matrices. Say we time a vector V in the middle, right? So, and that's what we call matrices does not commute when they multiply. And that's the end of the lecture. Okay. And we're signing off.